Stop what you're doing. Look around. Everything you see right now is impossible. Light from every object in this room is traveling in every direction simultaneously. Light from that wall is hitting your eyes. Light from your face is hitting that wall. Billions of light rays crisscrossing, overlapping, passing through the exact same point in space. And somehow, none of it gets mixed up. You see a perfect, clear image. But here's the part that'll break your brain. Right now, as you're reading this, radio waves from Moscow are passing through your skull. Television signals from distant countries are flowing through your chest. Radar from airplanes is penetrating your body. Infrared heat is radiating from your skin. X-rays from space are shooting straight through you. Cosmic rays from exploding stars billions of light years away are entering one side of your head and exiting the other. All of it, every single bit, is the same thing as light, just different wavelengths, all happening simultaneously, in the same space, through you, right now. How? How can billions of electromagnetic waves travel in every direction without turning reality into absolute chaos? And what is light, really? Because whatever they taught you in school was incomplete, possibly wrong, wrong in ways that actually matter. The truth about what light is and how it moves is so strange, so alien to everyday experience, that when you finally understand it, the whole world transforms. Let me show you. Picture a swimming pool on a summer day. People jumping in everywhere. Splash, splash, splash. Waves spreading across the surface, overlapping, interfering. Complete chaos. Now imagine a tiny insect floating in the corner, just feeling the water rise and fall. Waves hitting from different angles, different rhythms, different intensities. Could that insect, just from sensing vibrations, figure out what's happening across the entire pool? Who jumped? Where? When? Sounds impossible. But yes, all that information is encoded in the waves. And that's exactly what you're doing right now. When you look at anything, light entering your eye is waves. Three-dimensional waves traveling everywhere, crisscrossing, overlapping. A complete mess. Your eye is just an eighth of an inch hole, a tiny detector. And from this chaos, you extract a crystal-clear image of reality. Here's what melts my mind. When you're looking at me, someone to your left can simultaneously see someone to your right. Light going this way, light going that way. Waves in all directions. It's not arrows passing through each other. It's the electric field vibrating everywhere, like water rising and falling. The combination is so impossibly elaborate that you see me perfectly, completely undisturbed by the fact that someone else is seeing something entirely different using light passing through the same space. But that's just visible light, the narrow slice your eyes detect. Think about those pool waves again. Some are long swells, some are quick ripples. Your eye only responds to waves of very specific tiny lengths, about 100,000th of an inch. What about longer waves? Those are heat, infrared radiation. You feel them, but can't see them. Pit vipers can. They hunt mice in total darkness by seeing body heat. And the waves get longer. Radio waves. Same thing as light. Exactly the same, just longer wavelengths. Right now, Moscow radio is broadcasting through this room. Signals from Peru. Radar from planes. All flowing through your body constantly. Plus ultraviolet. Plus X-rays. Plus cosmic rays. All the same phenomenon, just different frequencies. Don't believe me? Pick up a radio. Turn it on. The electrons in the wire get pushed back and forth by electromagnetic fields oscillating at specific frequencies. Tune the dial. Suddenly, you hear Moscow radio. Voices. Music. It was there all along. You just couldn't detect it. All these waves passing through the same space simultaneously. You have to stop and think about it to really appreciate the inconceivable nature of it all. For centuries, brilliant minds fought over what light really is. Newton said particles, little bullets shooting through space. That's why light travels straight, he argued. Huygens said waves, like sound, like ripples in water. Waves spread out, interfere. They couldn't both be right. The argument raged for 200 years. Then came the experiment that seemed to end it. Shine light through two narrow slits. If light were particles, you'd see two bright strips on a screen, bullets going through holes. But that's not what happens. You see a pattern. Bright bands, dark bands, alternating. Interference. Exactly what waves do when they overlap. When wave crests meet, brightness. When a crest meets a trough, they cancel. Darkness. Light must be a wave. Case closed. Except then someone built a detector sensitive enough to catch individual photons. What happened? Click, click, click. Individual arrivals. Like particles, but send them through one at a time. Surely one particle can't interfere with itself. It does. The interference pattern still builds up. Each photon somehow goes through both slits like a wave. So which is it? Here's what they won't tell you in school. Neither. Light is not a wave. Light is not a particle. Light is light. We don't have a word for it because nothing in everyday life behaves this way. We use waves and particles as approximations, crutches for our imagination. The reality is stranger. Photons are real. You can count them. Detectors click, but they don't behave like bullets. They behave according to quantum mechanics, exploring all possible paths simultaneously. When you observe which slit a photon goes through, the interference vanishes. You get particle behavior, not because photons switch forms, but because asking which slit is a particle question. Ask particle questions, get particle answers. Ask wave questions, get wave answers. The photon doesn't decide. It's always a quantum object. What changes is how we measure it. This isn't philosophy. This is how nature actually works. If light isn't particles flying straight, why does it go straight? Here's the beautiful part. Light takes the path of shortest time. That's Fermat's principle from the 1650s. Of all possible paths from A to B, light takes the one requiring least time. Why does light go straight in air? Because straight is shortest distance, and at constant speed, shortest distance means shortest time. Why does light bounce off mirrors at equal angles? Because that's the fastest path from source to mirror to destination. Now it gets interesting. Light traveling from air into water. In water, light slows 25%. Imagine you're on a beach, someone's drowning 50 feet out. Fastest way to reach them? Straight line? No. You run faster than you swim. So run farther on the beach, even though it's longer, to minimize slow swimming time. That's exactly what light does. It bends at the air-water boundary, travels farther in the fast medium to spend less time in the slow one. This bending is refraction. Once you understand light minimizes time, strange phenomena make sense. Mirages on hot roads. You see what looks like water ahead, but it's bone dry. You're seeing skylight bent by hot air. Air above hot pavement is hotter, less dense. Light travels faster in thin air. So instead of coming straight down, light curves through the hot layer where it's faster, then bends to your eye. You see sky from the road's direction. Your brain thinks reflection, water, an illusion created by physics. Here's another. When you watch the sunset, the sun touching the horizon, it's already below the horizon. You're seeing a ghost. Earth's atmosphere is thin up high, dense below. Light curves downward, staying in thin air longer where it's faster. The sun appears on the horizon when it's actually well below it. We see phantoms. Let's make something useful. A lens. We want all light from point P to reach point P prime. Focus it. Light going straight, fine. But how do we make light going other directions also reach P prime? If light always takes the shortest time path, it won't take these different routes unless we make all paths take equal time. That's the secret. Glass slows light. So for rays traveling longer distances, we insert glass to slow them down, making up for extra distance with extra delay. Result: glass thicker in the middle, thinner at edges. All paths take the same time. That's a lens. Same for mirrors. Want to focus starlight from billions of miles away? Make a curved mirror shaped so light hitting anywhere takes the same time to reach the focal point. That shape is a parabola. The Palomar telescope uses exactly this. All optical instruments work by manipulating travel times. But here's the deepest question. How does light know which path takes least time? Does it check nearby paths? The answer is yes. That's where wavelength matters. The wavelength tells us how far light must check alternatives. Hard to show with visible light because wavelengths are tiny. But with radio waves, centimeters long, it's obvious. Set up a radio transmitter, receiver, and slit between them. Radio goes through. Make the slit narrower. Still works. Move the receiver sideways. Won't reach it through a wide slit. Why? Because waves check several paths, and those paths have different times. They interfere, cancel out, but close the slit to narrower than the wavelength. Now there's only one path. Nothing to compare against. The waves take it. With a narrow slit, more radiation reaches the sideways detector than with a wide slit. Try this yourself. Find a bright point of light, a street light or a sun reflection. Hold 2 fingers in front of one eye. Look through the crack. Squeeze your fingers together. The dot becomes a line. You'll see fringes, color bands. Why? Your fingers are close. Light spreads at an angle, enters from several directions. Light not going straight. Light checking nearby paths. Light behaving like a wave. So what's really happening? Here's the quantum picture. Light is photons, real particles. Detectors click, but photons don't travel like bullets. When a photon goes from A to B, it explores all possible paths simultaneously. Every path imaginable. For each path, calculate a little arrow. The arrow's angle is proportional to that path's time. Different paths, different times, different arrow directions. Add up all arrows for all paths. The probability of arrival is proportional to the square of the sum's length. Near the shortest time path, time doesn't change much with small path variations. Arrows point the same direction, reinforce each other. Far from shortest time, small path changes mean large time changes. Arrows point everywhere, cancel out in a spiral. Almost all probability comes from paths near minimum time. That's why light follows shortest time, not because it only takes that path, but because all others cancel through interference. This connects photons to classical optics, particles to waves, quantum to classical. Light comes in different wavelengths. Longest, meters to kilometers, are radio waves. AM, FM, TV broadcasts. Shorter, centimeters to millimeters, microwaves. Radar. Shorter still, fractions of a millimeter, infrared. Heat. Then visible light. 400 to 700 nanometers. Blue around 450. Red around 650. Shorter than blue, ultraviolet. What burns your skin? Shorter still, X-rays. Shortest, gamma rays from radioactive decay and cosmic explosions. All the same thing. Oscillating electric and magnetic fields. Only difference is wavelength. Radio passes through walls. Visible light doesn't. X-rays pass through flesh. Visible light doesn't. But it's all light. And it's all here now. Radio from thousands of stations. Infrared from everything warm. Visible light bouncing around. Ultraviolet from a sun. X-rays from space. Gamma rays from dying stars. All the same wave. All coexisting. All passing through each other without scrambling. An invisible network filling every point in space, including inside your body. So what is light? Not a wave. Not a particle. Light is light. A quantum object. When unmeasured, photons explore all paths, interfering like waves. When detected, they arrive as discrete quanta. Both are real. Both are true. No contradiction. Just 2 aspects of the same quantum reality. We evolved to understand rocks, trees, animals. Things we can hold. Light is none of those. Light is something else. But we can understand it by following the math, doing experiments, observing how nature actually behaves. And it leads somewhere strange and beautiful. Think about now. Photons from the sun, 93 million miles away. Infrared from everything around you. Radio from hundreds of stations. Ultraviolet. X-rays. Gamma rays. All passing through the same space, through your body. A tremendous mess. And yet we sort it out. Tune a radio, hear one station. Open your eyes, see clearly. Everyone knows electromagnetic waves fill space. But stop and really think about it. The inconceivable nature of nature itself. When you truly understand what light is, the world transforms. Sunlight through a window isn't just brightness. It's photons that explored every possible path, interfering, creating the illusion of straight rays. Shadows aren't blocked light. They're destructive interference. Rainbows are wavelengths separated by refraction. That's what physics is about. Expanding intuitions to grasp nature as it actually is. Seeing past surface illusions to deeper reality. Where light is neither wave nor particle, but something stranger. Where photons explore all paths simultaneously. Where past, present, and future weave together in ways we're still discovering. That's the beauty. The terrible, wonderful beauty of understanding. Now that you know what light really is, you'll never see the world the same way. Every lamp, every reflection, every sunset, you'll know what's really happening. And that knowledge is worth more than any comfortable illusion. So next time someone says they understand light, ask, wave or particle. Will they confidently choose one, you'll smile. Because you know the truth is far stranger, far more beautiful. Light is light, and the universe is more magnificent than we ever dreamed. Claude is AI and can make mistakes. Please double-check responses.